This kind of thing has been going on since the beginning of recorded history, and it's being amplified right now through our technological capabilities, our media capabilities. At first, scientists thought 3E Atlas was strange enough on its own. But 3 Atlas isn't traveling solo. Hidden in the darkness, there are 9 mysterious objects moving right alongside it, like an escort through our solar system. Nobody saw them coming, and nobody knows what they really are. Are they pieces that broke off? Are they something else entirely? One thing's for sure. 3E Atlas has company. And the fact that we almost missed them raises the biggest question of all. What else could be lurking out there still unseen? Earth and the galaxy's ancient past. 7 billion years ago, when 3I Atlas first formed, the Milky Way galaxy was a fundamentally different place. Star formation rates were dramatically higher. Chemical compositions were unlike anything in our current cosmic neighborhood. And the gravitational landscape that shaped stellar orbits operated under conditions that no longer exist anywhere in the modern galaxy. The comet was born in the galaxy's thick disk, a stellar population representing some of the oldest structures in our cosmic region. This ancient formation environment explains many of the bizarre characteristics that have been puzzling scientists since the discovery in July 2025. The distinction between the thick disk and thin disk regions of our galaxy is like the difference between a wild frontier town and a modern suburb. The thick disk formed during the galaxy's rowdy youth when star formation was happening everywhere at crazy rates and heavy elements were getting scattered around in completely different patterns than what we see today. Our solar system formed much later in the more civilized thin disk region where things had settled into more predictable patterns. Objects from the thick disk carry chemical signatures that are basically fossils from galactic prehistory. The metallicity levels back then were totally different. Fewer heavy elements overall, but distributed in ways that created formation conditions we don't see anywhere in our modern cosmic neighborhood. 3 Atlas is essentially carrying a sample of materials from when the galaxy was young and chaotic. The James Webb Space Telescope's analysis revealed that 3I Atlas likely formed near what scientists call the carbon dioxide ice line in its original protoplanetary disk. This represents a specific distance from its parent star, where temperatures dropped just low enough for carbon dioxide to transition from gas to solid ice, creating a zone where this compound accumulated in massive quantities. This formation location would perfectly explain the record-breaking carbon dioxide to water ratios that JWST detected. The most extreme chemical composition ever observed in any comet. The abundance of carbon dioxide in the comet's atmosphere could indicate that its core is intrinsically rich in this compound due to formation conditions that simply don't exist in our local stellar environment. The parent star system where 3 Atlas formed was likely much more energetic than our Sun, with higher radiation levels and more intense stellar processes. The comet's ices were potentially exposed to radiation levels far beyond anything experienced by objects in our solar system, creating chemical signatures that we're only now learning to interpret. The thick disk origin also places 3I Atlas among materials that formed when the galaxy had different metallicity levels and chemical enrichment processes. Heavy elements were distributed differently throughout space during that era, affecting how planetary systems developed around ancient stars in ways that challenge our models based on local experience. The impossible galactic odyssey. The journey that brought 3I Atlas from its ancient birthplace to our solar system is absolutely mind-blowing when you really think about what this comet has been through. We're talking about a 7 billion-year road trip through some of the most dangerous neighborhoods in the galaxy. And somehow this ancient iceball made it to our cosmic doorstep in one piece. Bryce Boland from Eureka Scientific, one of the few astronomers who has studied all 3 known interstellar objects, puts it perfectly when he explains how complicated the galaxy really is. It turns out that the galaxy is quite complicated. It's not like you have all the stars in the galaxy orbiting one central thing like a star, a supermassive black hole. They do in a way, but the gravitational potential is quite variable in the galaxy because it's huge and has irregularities. Molecular clouds, spiral arms, stellar clusters. Think of the galaxy like a massive pinball machine where the bumpers and obstacles keep moving around. 3 Atlas has been bouncing through this cosmic pinball game for billions of years, getting knocked around by giant molecular clouds, spiral arms packed with young hotstars, and stellar clusters that can gravitationally kick objects in completely new direction. During its incredible journey, this comet probably completed dozens of laps around the galaxy's center, with each circuit taking about 200 million years. That means while 3 Atlas was making one orbit, entire dinosaur species were evolving and going extinct on Earth. Every single orbit exposed it to completely different cosmic environments, sometimes cruising through the relatively empty spaces between spiral arms. Other times getting blasted by radiation from massive star-forming regions. The comet survived encounters with molecular clouds. These are absolutely massive regions of dense gas and dust that can span hundreds of light years. Getting too close to one of these things can gravitationally disrupt a passing object or strip away surface materials. Yet 3I Atlas came through these encounters with its structure intact. But here's what's really crazy about trying to trace this journey. The galaxy is so chaotic over million-year timescales that it becomes nearly impossible to figure out exactly where this comet has been. Bolin explains the challenge. Over millions of years, an object could encounter spiral arms and all sorts of things that can really throw off its trajectory in the galaxy. And so I think it's really hard to say anything about an interstellar object's trajectory beyond maybe 1 or 2 galactic orbits. For something billions of years old, like I've seen some papers state, its trajectory and origins are pretty hard to pin down. So we know 3I Atlas came from the ancient thick disk region, but its exact path through the galaxy over billions of years is basically impossible to reconstruct. It's like trying to trace the path of a pinball that's been bouncing around a constantly changing machine for thousands of games. The chemistry that survived everything. Here's where things get absolutely wild. With 3I Atlas, not only did this comet survive a billion-year journey through galactic hell, but it somehow managed to preserve chemical signatures that should have been destroyed ages ago. The compounds that JWST detected in this thing shouldn't exist after what this comet has been through. On August 6, 2025, when the James Webb Space Telescope aimed its incredible infrared vision at 3 Atlas, scientists weren't just looking for ordinary comet chemistry. They found something that blew their mind. Not only the highest carbon dioxide to water ratio ever seen in any comet, but also carbonyl sulfide, a molecule so fragile it's like finding a glass sculpture intact after it spent billions of years getting tossed around in a rock tumbler. Carbonyl sulfide is the kind of compound that normally decomposes when exposed to cosmic ray bombardment over extended periods. Finding it intact in 3I Atlas after billions of years of space travel is like discovering a snowball that somehow survived a trip through a blast furnace. Either this comet has some kind of incredible internal protection system or there are chemical processes happening inside it that we don't understand at all. Luis Salazar Manzano from the University of Michigan made another discovery that makes the chemistry puzzle even weirder. His team found that 3 Atlas shows severe carbon chain depletion. It's missing way more C2 and C3 molecules than any other comet we've studied. This is backwards from what should happen during billion-year journeys through space where these molecules should gradually accumulate like cosmic dust bunnies. But wait, it gets stranger. The comet is also producing cyanogen, which typically forms through reactions involving those missing carbon chain molecules. So 3-2 Atlas is somehow making cyanogen while being severely depleted in the compounds that usually create it. It's like finding a car running perfectly on gasoline while having an empty gas tank. The water, ice, carbon monoxide, and other volatile compounds that JWST detected should have sublimated away or been chemically altered during the comet's galactic travel. Yet here they are, preserved well enough for our most advanced instruments to detect and analyze. Either 3I Atlas spent most of its journey in incredibly cold, stable conditions far from any stars, or it has internal characteristics that actively protect these materials in ways we've never seen before. The chemical fingerprint of this comet is basically a direct sample of materials from when the galaxy was young and operated under completely different rule. Most of what we know about ancient galactic chemistry comes from computer models and indirect observations. But 3 Atlas is carrying actual physical evidence of conditions from that era. Surviving billions of years of cosmic hell. The fact that 3I Atlas made it through its galactic journey in one piece is honestly miraculous when you consider what this comet has been subjected to over billions of years. Most objects wouldn't last a fraction of this long under the kinds of conditions this ancient wanderer has endured. For starters, cosmic ray bombardment over billion-year timescales should have fundamentally scrambled the internal chemistry of anything traveling through interstellar space. These high-energy particles slam into objects and break apart molecular structures, gradually altering the composition of materials exposed to them. Yet 3-2 Atlas has maintained chemical signatures that scientists can still analyze and interpret. Then there are the gravitational encounters that should have ripped this comet apart completely. During its journey, 3 Atlas likely had close encounters with massive objects that could generate tidal forces strong enough to disrupt its structure. The fact that it's still holding together well enough to show organized outgassing and dust ejection suggests either incredible luck or internal properties that resist normal destruction mechanisms. The thermal cycling this comet experienced over cosmic timescales is another factor that should have destroyed most materials. Passages through different galactic environments would have subjected 3I Atlas to dramatic temperature swings from near absolute zero in the empty spaces between stars to potentially much higher temperatures during encounters with stellar regions. Most materials undergo significant physical and chemical changes under such extreme thermal stress. But here's what's really amazing. Not only did 3-2 Atlas maintain its structural integrity, it also preserved organized internal structure sufficient to support the kind of activity we're seeing today. The dust particles it's ejecting are hundreds of microns across, much larger than typical comet dust, suggesting internal binding forces that are way stronger than normal ice-dust mixtures. Bryce Boland describes the current activity levels in a way that hints at how this ancient structure might be different from normal comets. Based on this information, we think dust is leaving the comet at a very slow speed, about a meter/s. This suggests that the comet may be weakly active right now. This weak activity compared to solar system comets might reflect how billion-year exposure to galactic conditions has changed the comet's internal properties. The tail drama. One of the most visually striking things about 3-2 Atlas is how its tail behaves in ways that make absolutely no sense according to everything we know about comet physics. Instead of pointing away from the sun like every other comet we've studied, this ancient visitor's tail points directly toward our star, which is basically impossible according to the textbooks. Normal comet tails happen because solar wind and radiation pressure push ejected dust and gas away from the sun's direction. This is such a reliable process that astronomers have historically used comet tail directions as natural indicators of solar wind conditions throughout the solar system. It's like having a cosmic windsock that always points in the direction the solar wind is blowing. But 3 Atlas is doing the complete opposite. Its tail material is being ejected toward the sun, which means either the dust particles are way too heavy for solar radiation pressure to affect them, or there are physical processes at work that we don't understand. Explains what's happening. The 3I/T is quite interesting in the sense that the tail is going in a strange direction. Comet dust, when it gets ejected into space, is usually blown in the direction opposite to the sun due to solar radiation pressure. But curiously, this is not what we see for 3I/ATLAS. Instead, its tail is going in the direction of the sun. The explanation involves dust particles that are hundreds of microns across, significantly heavier than typical comet dust. These particles are too massive for solar radiation pressure to push around like normal comet material. So, when the sun-facing side of the comet heats up and starts ejecting material, the particles just drift toward the sun because solar radiation isn't strong enough to overcome their momentum and push them in the opposite direction. The incredibly slow ejection speed of about 1 meter per second is also weird compared to normal comets, which typically blast out material at hundreds of meters/s. This suggests that 3E Atlas is either weakly active compared to solar system comets, or that its internal structure creates completely different ejection mechanisms than what we're used to seeing. This tail behavior might be related to the comet's incredible age and the structural changes that accumulated during its billion-year journey. The larger, heavier dust particles suggest internal binding forces that are much stronger than typical ice-dust mixtures, possibly created through processes operating over cosmic timescales. The trajectory that revealed ancient secrets. The path that 3I Atlas is following through our solar system provided the crucial evidence that revealed just how incredibly old and ancient this visitor really is. The trajectory analysis is like cosmic detective work that traces this object's origins back through billions of years of galactic history. The steep angle at which 3 Atlas approached our solar system immediately told astronomers that this wasn't just another typical interstellar visitor. Objects following such trajectories don't come from our local galactic neighborhood. They originate from much older, more distant regions of the galaxy with completely different orbital characteristics. When researchers traced the trajectory backward through galactic space, they discovered that 3I Atlas comes from the Milky Way's thick disk region, which is like finding out that your houseguest is actually from ancient Rome. The thick disk formed during the early epochs of our galaxy's evolution, when conditions were dramatically different from anything in our current cosmic environment. The mathematical precision required for this kind of trajectory analysis over billion-year timescales is honestly mind-blowing. Researchers have to account for the gravitational influence of our Sun, all the major planets, the complex gravitational potential of our local galactic region, and the effects of things like solar radiation pressure and outgassing. The fact that the trajectory clearly points back to the thick disk demonstrates just how reliable these calculations can be despite the enormous scales involved. But here's what makes the trajectory analysis even more fascinating. It helps explain why 3 Atlas has such weird chemical properties. Objects from the thick disk formed under conditions that don't exist anywhere in the modern galaxy, which perfectly accounts for the impossible chemistry we're seeing in this ancient comet. Bolin notes an exciting opportunity that the trajectory creates. 3I/L is actually going to get quite close to the orbit of Mars, which could be an interesting opportunity for spacecraft at Mars to try and observe this thing. I'm a fan of it. I think they should give it a try. This Mars encounter could provide multi-angle observations that are impossible to obtain from Earth-based telescopes. The trajectory also creates the timing constraints that make studying 3I Atlas so urgent. The comet will be observable until late August or early September 2025, but then it disappears behind the Sun during solar conjunction when Earth moves around its orbit enough to see past the Sun again. 3I Atlas will reappear for its closest approach in December 2025. Humanity's final chance to study materials from the early galaxy. The size mystery. Figuring out exactly how big 3I Atlas actually is has turned into a fascinating detective story that perfectly illustrates one of the biggest challenges in studying active comets. The comet is surrounded by so much dust and gas that measuring its actual nucleus is like trying to figure out the size of a cat that's buried under a massive pile of fur. Bryce Bolin has the perfect analogy for this problem. It's like looking at a fuzzy cat. Have you ever seen a big fluffy cat after it goes to the groomer and it gets a buzz cut? When I was a kid, we had a Persian cat and my mom had allergy, so he would have to get a haircut. This big fluffy cat. And after the buzz cut, it's a lot smaller. Ground-based telescopes are like looking at the fluffy cat version of 3 Atlas. Earth's atmosphere smears the image, and all the dust and tail material surrounding the comet's nucleus creates a fuzzy blob that makes it nearly impossible to separate what's actually comet and what's just surrounding material. Space-based telescopes like Hubble are like giving the cat that professional buzzcut without atmospheric interference. You can resolve the actual nucleus from all the surrounding dust and tail material. David Jwitt at UCLA used Hubble specifically to get this clear view of 3I Atlas, allowing much more accurate measurements of light coming from the actual comet nucleus. Scientists are using 2 different approaches to estimate the size. The first method compares 3I Atlas's brightness to other interstellar objects we've observed at its current brightness of about 17th or 18th magnitude, located roughly 3 to 4 astronomical units from the Sun. It appears significantly brighter than 2I Boris was at similar distances. Since Borisov had an estimated nucleus diameter of a few hundred meters, the brightness difference suggests 3 Atlas might have a nucleus about a kilometer across. But the second approach, using high-resolution space-based imaging, could reveal a very different story. If the nucleus turns out to be smaller than brightness measurements suggest, then 3I Atlas might be much more active per unit surface area than normal comets, which would be another unusual characteristic of this ancient visitor. This size determination work is crucial because activity levels, chemical composition analysis, and evolutionary history all depend on knowing the actual nucleus size. The fuzzy cat problem affects almost every aspect of studying 3 Atlas. From understanding its internal structure to interpreting the chemical signatures detected in its surrounding atmosphere. The final chapter of 3 in Atlas's epic galactic journey is playing out right now in our solar system, creating unprecedented scientific opportunities while revealing the last details about this ancient visitor's incredible odyssey. The comet's path through our local neighborhood provides the culmination of billions of years of cosmic travel. That's it for today. Let us know your thoughts in the comments down below. And don't forget to like and subscribe for more content on 3Y Atlas.